Good evening, everyone. Alright, well, sorry it's been a while. I got a little busy with trips and stuff like that, but we're back and we're starting where we left off, which is operations with rational expressions. I'm going to try and do a little bit and finish the whole prerequisites chapter for this Christmas stream. Merry Christmas. So let's start with this. Operations with rational expressions. So where we left off was simplifying rational expressions, but now you have multiplication and division. So we're going to start with example 4. Remember, all of this is going into a presentation, so there will be a much more concise and less stream of consciousness version of this once I get all the animations going, which I'll probably stream another session on doing the Manim or PowerPoint, messing around, seeing what looks good. So example 4 is 2x squared plus x minus 6 over x squared plus 4x minus 5 times x cubed minus 3x squared plus 2x over 4x squared minus 6x. I know my writing is terrible, so we're going to try to make it a little write slower and make it a little easier. Okay, so the first thing is we want to look at this guy and see how we can factor him. So we know that if we can factor him, that, remember, like we said before, we're trying to get a 1x there. So if we think of FOIL, we can see how we can get a 1, and we're going to have a 2x and an x, because that's the only thing that can make a 2x squared. And then on this side, we're going to have either a 6 and a 1 or a 3 and a 2. So if we say 2x, I think it's going to be 2x plus 3. No. Yeah, how about this? Minus 3, and here we're going to have a plus 2, because 2 times 2 will give us 4x, and then minus 3 times x will give us minus 3x, and that gives us a 5. So that's how we solve that one. So we know that that one can be written as 2x minus 3 times x plus 2, and the bottom is going to be factored. Let me write that x. It's going to be x and x, so we know there's going to be an x, and there's going to be an x. It's minus 5, so we need a minus and a plus. And you can write the minus and the plus here because it doesn't depend on the first value here of a 2 being that, so we can put them either way here, whether the plus comes first or the minus. Here it looks like it's going to be plus 5 minus 1. And then how do you factor the second one? That's going to be times, well, there's no constant term, so we can already factor out an x, and then we have the remainder polynomial, which would be x squared minus 3x plus 2. So that's the plus here and the minus here means that it's both minus, and it's minus 2 minus 1. So that'll give me x squared. You can't see what I'm writing here. That'll give me x squared minus 2x minus 1x, which is going to give me minus 3x squared, or minus 3x rather, and then plus 2, because minus 2 times minus 1 is plus 2. So that's the correct factorization there. Then we have on the bottom a simple 4x squared minus 6x. So if you factor out a 2x from that, you get 2x times a 2x, which will give us 4x squared, minus a 3, which will give us the 6x. So here we can see that that will cancel out with that. This x minus 1 will cancel out. In fact, I like to use different colors, so this x minus 1 will cancel out with this x minus 1. It may not show up as that blue, but one was black and one was blue. And then the others are fine. The only other thing I would note here is that this x plus 2 term and this x minus 2 term is going to give us a difference of squares, right? So we can simplify this as x squared minus 4, which is 2 squared. That'll get rid of this term. And I say get rid, but it's not necessarily get rid. It is a it allows us to say that we've completed what those will end up as in the product. We're not getting rid of it, it's just there. And then so that's going to be multiplied by x because the x is still here. Remember, when you multiply, you just multiply the tops and you multiply the bottoms, the numerators and the denominators, and that's what you end up with. So on the bottom you'll have 2x, and then you'll have x plus 5. Now, I do see a mistake that I made, which isn't necessarily a mistake because math still works out. Here, this x will cancel out with that x. The mistake would be that it could cancel out up here. There's no reason that you couldn't do that earlier rather than later. So if we do it up there, then we don't need it down here, and the end result is just x squared minus 4 over 2x plus 5. Now, remember that here we know that x cannot equal 5 in the resultant thing. However, we do need to go back and look above and say, well, x can't equal 0. X can't equal 3/2. And x can't equal positive 1 either. And that will be right again. Those should be assumed by looking at the way the equation is, but stickler teachers will count you off. And it's not that x can't equal 5, it's x can't equal negative 5. So there you go. The next example, just another quick one, would be division instead of multiplication, which we're going to use a trick to make it even simpler. Would be x cubed minus 8 over x squared minus 4 divided by x squared plus 2x plus 4 over x cubed plus 8. Now remember that when you divide a fraction by another fraction that is the same as multiplying the fraction by the reciprocal of the and that's not times or equal to, that is the underlining of the times so that people understand that now instead of division we have replaced it with multiplication. So I can get rid of that line now that we've seen it. And then you would just take the reciprocal of this, i.e. invert the fraction. It's 2x plus 4. That's a 4 even though it doesn't look like it. And so now you'll note that these things will multiply to a difference of squares. Makes it very easy. It doesn't do it that way, but you could. And then on the bottom, you would want to factor out, you would want to factor both of them out, just so we can see if we can cancel anything. And a lot of times what you'll do is you'll simplify it into terms of only a single x or less. So those are perfect cubes, so he actually simplifies it as a perfect cube. So plus 2x plus 4. And remember, with cubes, you can do the same thing for the other one. It's just with squares you can't do it with both difference and sum. So you would just do that, and then they're still being multiplied, right? X squared minus 4 is the same as x minus 2 times x plus 2, and this is why he does it this way. And then this is going to be x squared plus 2x plus 4. That's going to be just x squared plus 2x plus 4. And magically, look at that. That looks very much like this one. So we're going to cancel those out, and we'll use a green this time so you can see it. And even still, x plus 2 over here looks like x plus 2 over here. So when you divide all that through, you just end up with x squared minus 2x plus 4. Knowing that we had fractions before, we know that x cannot equal plus or minus 2. And that solves that. So remember that division can be handled as just the multiplication of the inverse. That solves a lot of them. He talks about subtracting rational. We went through multiplication and division. That's pretty easy, quote, when it comes to this stuff, but 6. If we look at subtraction, x over x minus 3 minus 2 3x plus 4, if you remember your fractions, what you would do is least common denominator, or you could just do the classic, we're going to multiply this by this, 3 plus 4 over x minus 3, and then multiply the other one, subtract, times x3 plus 4, and then 2 times x minus 3. That's going to be equal to 3x squared plus 4x minus 2x plus 6 over x minus 3 times 3x plus 4. If we look at the top, these two will give us 3x squared plus, plus 2x plus 6 over x minus 3 times 3x plus 4, and I don't think that that can be simplified any further. None of the factors of that are the same down here. Because 4 doesn't go into 6, so it's not going to be that, and none of the terms are negative, so it's not going to be a minus 3. So that is, that is where we end this one. Alright, then if you have a compound fraction like this, say 1 over x over 1 over x squared plus 1. There's an example. I'm not going to go through it. The thing is that this is the same as saying 1 over x times 1 over x squared plus 1. So it's divided by, and so it's the same as the example that we had before, where you would flip this guy and multiply. The way I've always looked at it, just as another way of looking at it, is anything that is on the top in the numerator of the denominator. If you look at this, this is the numerator, this is the denominator. So if you're in the numerator in the denominator, right, then that just goes to the bottom fraction overall, right? So this 1 would come to here, and then this one would go here. That's the same as doing it here, right? So 1 over x, you take the reciprocal, so now we're multiplying by x squared plus 1 over 1. These two will be multiplied, these two will be multiplied, and it achieves the same effect as doing that. As we go through examples, it'll be much clearer. Just remember that when you have a compound fraction like that, Usually they'll be in parentheses, so you know what belongs on top and what belongs on bottom. And that this bar just means divides by. So it is the same as writing it this way. That it's not to throw you off. It is a fraction. I mean, 2/3 is literally 2 divided by 3. And so it's just an alternate way of writing and knowing what the notation means and understanding ways of solving it that way. Now, one thing that you'll see that this relates to, and this example we will do, is example 9. You have x times 1 minus 2x to the negative 3/2 plus 1 minus 2x to the negative 1/2. Now, remember that negative exponents means inverse. It's the same, like we're talking about it, like the reciprocal, right, of that exponent. So if we rewrite this, which would be the first step, is x divided by this guy without the negative sign. So we have 1 minus 2x, and that whole thing is to the 3/2, right? That's how you would rewrite this guy. And then we're going to rewrite the second guy as just 1 divided by 1 minus 2x to the 1/2. Notice there's no negative signs now, so we've gotten rid of all the negative exponents by putting everything where it belongs. If you had something divided by a negative exponent, that would then come to the top, right? So just as a side example here, if you had like 3 divided by 2 plus x, and that's going to be to the negative 1/2, that's the same as 3 times 2 plus x to the 1/2. So if it's a negative exponent, you just change where it belongs. If it's in the numerator, it goes to the denominator. If it's in the denominator, it goes to the numerator. That will just come with experience. So here, we notice that these two terms are the same. The polynomial inside is the same. So the least common denominator is actually going to be, we have x over the same thing, right? Because that is the least common denominator. And then to get to that common denominator, we look at the fraction and we say that this, to get to this guy to 3/2, we have to multiply it, we have to add, 1 to it. Because 1 plus 1/2 will get us to 1.5, which is 3/2. To add 1 to it, we just multiply it by itself, right? So we're going to multiply it by 1 minus 2x. But whatever we do to the bottom, we have to do to the top. So we're going to, if we were to write it out in a way that you would see it, you would say plus, and you would say 1 minus 2x over 1 minus 2x times 1 over 1 minus 2x to the 1/2. And that's in parentheses. These technically should be in parentheses as well, but they don't have exponents, so you don't have to write them in parentheses. When you do that, it's very simple. This goes to the 3/2, and this multiplied by 1 is just itself. So we have x over 1 minus 2x to the 3/2 plus 1 minus 2x over 1 minus 2x to the 3/2. Now that the denominators are the same, you can just add the top, x plus 1 minus 2x over that common denominator to the 3/2. Well, minus 2x plus an x is just going to give us x. So we have x plus 1 over 1 minus 2x to the 3/2. And that is as, I did that backwards. You are right that 2x plus x, 2x minus x will give us 1, but it's minus 2x. So you actually have 1 minus x instead of 1 plus x. That is simplified, so this is how we get to that. like I say, as you do more of these problems, everything will become clearer. When we go through the presentation or the videos on the topic, it will be a lot more well explained, and you can always ask questions in the comments. That's a little bit weird, but okay. That's gonna do it for this chapter. When we go through the problems, we will go through a lot more, and the explanation will be a lot more drawn out. That way, when we do all the problems, people understand a little bit better what that is. So all of that's going to be on the presentation, and now we can move on to P.6, Errors and the Algebra of Calculus. So here, now I don't assume that you're in calculus. I don't believe you have to know about calculus, but this algebra book is in prep for going into calculus. So you'll go to pre-calculus, you'll go into trigonometry, geometry, and other things that allow you to go further. I will be going from here to those maths. The whole point of this channel is actually going to be engineering classes like statics, thermodynamics, etc. But I'm trying to do the math fundamentals so that if you have questions on those videos, I can direct you to the math videos to study the math part. By the time those videos come along, I will likely just fly through the math, because I'll assume that getting to that point you'll already have taken this part, as most engineering schools do, and I won't be, I don't want to say wasting time, but I won't waste the time for explanation of math related questions in the engineering courses. That would be mostly engineering stuff. Now there will be some discussion of math tricks or other things that would be used in certain problems or areas, but as far as simple algebra and stuff like that, yeah, that's best relegated to videos like this one. Okay, so here are algebra errors that many beginners fall into, many traps that beginners fall into, because the algebra is, it seems to be correct, but when you reveal it, it turns out to be incorrect. So be very careful with these. So one of the first easiest ones that trap people all the time, and we talk about this, is that A minus the quantity x minus b is not equal to A minus x minus b. Remember that you have to distribute the negative sign into the parentheses. So the negative, you get A, that is incorrect. We're going to write the correct form in, what color do I want? Light blue. Okay, I'm going to make this light blue. I'm going to write the correct version in light blue. So you have A minus, and then the minus gets distributed, right? So you have, you could say, we're going to change it to plus, and we're going to distribute the negative sign. Minus x, and then minus a minus b, right? And that turns into a minus x plus b. So that's what's going to throw people off, is that second minus sign, this guy, turns into a plus sign when you distribute the first minus sign through that parenthetical quantity. Okay, so that's error number 1. Error number 2 is going to be that a plus b squared is not equal to a squared plus b squared. And this is particularly insidious because there's little tricks you can do with a difference of squares and nice things, but remember that you gotta remember your FOIL, right? And so if we FOIL it out, we have a plus b times a plus b, and you get a squared and you get b squared. Those are absolutely part of it. But you also have an a b plus an a, I'm sorry, plus, go back, plus an ab. So you have plus 2ab. So always remember that there is a middle term that is not to be neglected, and you won't make that mistake. So the third one is that 1/2 of a times 1/2 of b is equal to 1/2 times a times b, or just ab over 2, right? That's incorrect, because while you'll get used to factoring out or pulling out a 1/2 in polynomial equations or addition type equations, right? In this one you can absolutely pull out 1/2. But these are multiplications, and because of that you cannot factor out a 1/2 from those terms. You actually multiply them as if they were the term itself. So instead of 1/2 a, let's rewrite this as a over 2 times b over 2. And while the temptation to factor out the 2 might be there, they're multiplications. You can't factor it out, so you just multiply the tops and multiply the bottoms, and you'll see that there's a factor of 2 missing because it's a multiplication, so not an addition. So the correct answer is actually ab over 4, not ab over 2. All right. So the last one in this group, which they've grouped as errors involving parentheses, is, nope, I did not say that. What's wrong? 4. 3x, okay, that's a good one. 3x plus 6 squared is not the same as 3 times x plus 2 squared. The reason is, while you can factor the 3 out of the polynomial inside, because this parenthetical expression is squared, you cannot factor it out of the square. Now, if you're in advanced equations, or you feel that you've learned more, I don't mean for this to be confusing, but this is just the answer of why you can't do it. Let's take a look at 9x plus 18, right, squared. Now if I look at this equation, and while I leave everything in the bigger parentheses of the square, which I'm going to write bigger so it's apparent, you have 9 times x plus 2. Because I factor a 9 out from the 9x, and I factored a 9 out from the 18. Now I can take this 9 outside the parentheses, remembering that it's squared. So if I take it out of the square parentheses, I have to take the square root of it. So I can factor it out to a 3 if I take it out here, because it's been squared. And so if we go back to this guy, and we look at it in the light blue, right, we say that we can factor the 3 out of this expression, but then it's squared. So, actually I did that wrong. Ignore that last part of the video here. Oh man, I'd have to edit that out. I was thinking the other way. if it would be squared, right? So the 9 actually comes in here. So remember that when something in the parentheses looks like this, it's multiplied together. You can distribute that square amongst the things, and this would actually be, we're in blue here, 3 squared times x plus 2 squared, and now you would have the 9. 9 times x plus 2 squared. The other way around, instead of the square root. If you factor the square root, you'd have to square root it. Because this is squared, you would actually square it. So you could factor it out, but you have to remember to take the square. That's why this 3 is not squared, and that's why it's incorrect that way. But don't make this mistake. And then don't make the mistake that I made where it was square rooted. So those are the ones involving parentheses. We'll put a little parentheses here. Now we have problems involving fractions. And these trip a lot of people up. So we're going to go through them a little bit slower. Okay, so the first one is, you know that a over c plus b over c is equal to a plus b over c. Because we have a common denominator, we can add the tops. The reverse is not true. Where if you have a over x plus b, you cannot take it back out to a over x plus b over, a over b. Let's rewrite that. Because you cannot add denominators the way you add numerators. So we had a over c plus b over c. I really should have written that as a plus b over c, and then tried to split it out, which you can, a over c plus b over c. You can go either way, right? That turns into that turns back into the other way. But you cannot do that with this guy. This is incorrect. And the reason is because we can't split out denominators. You just leave it as this guy. There's nothing to be done. This is in its simplest form. Okay, so that's error number 1. Error number 2, we just talked about this. X over a divided by b is not b times x over a, because we division is the reciprocal blah blah blah. You might think, okay, I'm going to take what's on the bottom and move it to the top. Remember, what's on the top of the bottom moves to the bottom of the top. It's always reciprocal. So if you go by my rule of just quick thinking, you have x divided by a, all of that divided by b. The top of the bottom becomes the bottom of the top, and the bottom of the bottom becomes the top of the top. There's nothing on the bottom here. It would be b divided by 1, so there's nothing to worry about there. But the correct answer would be x over ab. And that's, again, my quick way of doing things. If you wanted to do it the more explanatory way, you would say that you have x over a divided by b, big divided by b. You put parentheses if you want. Now that's going to turn into a x over a divided by b, or b over 1, however you want to do it. Remember that that's the same as x over a times the reciprocal times, not x, but circle, times the reciprocal of the second one. And when you do that, then you just get x times 1 over a times b. And so you end up with the same thing either way you do it. All right. Then you have this is the same this is the same thing as the first one, but I guess they restate it. 1 over a plus 1 over b is not equal to 1 over a plus b. Is exactly the same as the first one. That's what they tried to do here. But what you would do here to get the right answer is common denominators, right? So you'd have the first one is b over b times 1 over a plus a over a times 1 over b. And that's going to be equal to b over ab plus a over ab. And that's going to be equal to a plus b over ab. And I wrote it as a plus b because normally we alphabetize things left to right, even though here it would be b plus a. That's no less correct to say b plus a over ab. It's just I'm so used to alphabetizing everything, I write it as a plus b because we can use the transitive property or commutative, I don't remember what it is exactly, and reorder things. Addition polynomial terms we can reorder like that. Okay, so another one that gets beginners would be 1 over 3x is not equal to 1 over 3 times x. And just think of it that way. 1 over 3x would not be the same as x over 3. You just think about it a little, because that is equal to x over 3, and that would look weird to say 1 over 3x is equal to x over 3. What really gets people here is less that they think they can take the x out, but when you read it, your brain reads 1 over 3 times x, and then you write 1 over 3 times x. So when you think about it, try thinking about the 3x as a single term and not 3 times x. Think of 1 over 3x, and you won't make this mistake as much. But some people may still make the mistake just because they think they can pull the x out of the bottom like we do out of the top. The reason we pull it out of the top is because we want to use the 1/3 as a coefficient and add it to other coefficients of x to the 1, and so you'll see that, and you'll have the desire, the urge to do it. The right way to write it here, and I'm not going to write it in blue because you would not normally write it this way, is 1 over 3 to the x to the times x to the negative 1. That is correct. But you have to remember that since the x is on the bottom, you have to use a negative exponent, and people don't really like to deal with negative exponents, so you likely wouldn't write it that way, which is why I didn't write it in blue. So the correct thing is just to remember that 1 over 3x, without writing it with a negative exponent, is the same as 1 over 3 times 1 over x. So that would be, which is the same thing, but it's a different way of writing it that more people are used to. Okay, so that's that one. Then you have here, it's the reverse of that error, right? So you have 1 over 3 times x is not equal to 1 over 3x. Now, the way they've written it makes it more, like you're saying, well, why would you ever make that mistake? Well, the way they wrote it was like this, 1/3 times x. And so your brain is going to associate that 3x as being together, and you may try and write it as 1 over 3x. So while I wrote it like this initially, that's, again, I'm very used to writing it fractions like that. I don't use this slash to do a fraction. But especially in the age of computers and everything, you'll see 1/3 to mean 1 divided by 3, and if you do read this fast enough, you have 1 over 3x. Sometimes you'll forget to say times, or you will say times. You say 1 over 3 times x, and you'll forget, hey, that's in a parentheses, as you're writing and then or transcribing it. So you have to be very, especially when you're talking to other people, you have to be very descriptive of what you're trying to say. So here I would say, I wouldn't even call it 1 over 3 times x. I would just say x over 3. But yeah, those two things are not the same. Again, when we write it, you would say that 1 over 3 times x is the same as x over 3. 1 over 3 times x. So you could write it like that. I would always just say x over 3 because it's very explicit. Now if you had 2 over 3x, it's 2x over 3. It's just make it very explicit what you're trying to portray in a mathematical way. So now the next one is a very similar mistake. I almost don't want to go over it because it's just too similar. You have 1 over x, and they've written it with the slash again. They even say be careful using the slash. It's not that, it's just knowing what you're trying to write. Plus 2, that's not equal to 1 over x plus 2. Again, saying it out loud might give you that impression. Hey, 1 over x plus 2. Well, yes, you could interpret that as 1 over x plus 2. And sometimes I'll use speed to indicate the terms. So 1 over x plus 2 means x plus 2 is together. If I say 1 over x plus 2, that pause that I say is meant to indicate that it's 1 over x as a fraction plus 2 by itself. I know sometimes that's not helpful. If you're not reading the screen, you might see it one way or hear it one way, but that's just me doing these videos. When you're talking to other people, your classmates or anyone that you're trying to give this information to, just be very explicit. And remember that anytime you see parentheses, you can always say the quantity of. So, or I would say it after. So 1 over x quantity plus 2, or the quantity of 1 over x, and then plus 2. Or one way to do it would be, well, that wouldn't work either. I would say 2 plus 1 over x, or 2 plus the quantity 1 over x. 2 plus 1 over x still may give you something like this, 2 plus 1 over x, and you may not understand it. Now, the thing to note here would be, why would you have 2 plus 1 over x? Normally, when you're conveying ideas to people, you're conveying them in the simplest terms, and 2 plus 1 would have been simplified to 3 over x. So when you hear 2 plus 1 over x, you can likely assume that the person telling you that is trying to say 2 plus the quantity 1 over x, or 2 by itself plus the fraction 1 over x. Again, so this is wrong, so we're going to do the right way. If we do this, it's 1 over x plus 2, and you could say over 1, which is going to be common denominator. Well, x is the common denominator, so we're only going to multiply the second one. 2 times x over 1 times x, and then you have 1 plus 2x over x. That is the simplified form of that. Oh, I lost my sharing. Give me a second here while I get it back. I don't know why it's not letting me share my screen. Give me 1 second. Alright, we're back. You saw my Chef Jean-Pierre video. Alright, so that's errors involving fractions. Okay, let's look at the errors involving exponents. So come back here, and I'm going to split this off and say involving exponents. Okay, so again, you should really not necessarily memorize, but understand these things internalize all this stuff so that it becomes second nature. This is what ends up killing a lot of students when they try to take tests and they don't have this stuff innate. They try to memorize things, and then when the test comes, that memorization doesn't fail them, but it's very tough to memorize these formulas and then try to apply them in the middle of a test. What you really do have to just get this internal and second nature, because these little mistakes will get you the points taken off that will cause you to fail classes like this. Because the problems that professors give you are meant to trip you up on these things. And it's an unfortunate reality of these classes that's how they design the tests, but they just want to make sure that you know these things so that as you get into the higher and higher level things, like calculus or engineering classes or technology classes, that these things don't trip you up. So, and again, I've made these mistakes many times. It's not, when I was a young student, these things are you're learning, and these things don't come easy because your brain isn't taught to think this way. You have to really get into the math rigmarole to understand this stuff. Okay, so first one would be x squared cubed is not equal to x to the 5. Now, we've talked about how exponents add up, and we've talked about how exponents multiply. You have to remember that exponents add up when it's the same thing being multiplied. That x squared times x cubed would be x to the 5. Because it's not that, if you want to think about it, we have x squared cubed, which means we have x squared times x squared times x squared. And because now we're having the same thing multiplied by itself, we can add. And so this would be 2 plus 2 plus 2, which would be 6. The other way, and this is what you should have internalized, is that these two things, whenever you take something that is exponentiated and you exponentiate it again, you multiply those things. So you can see there's 3 2's that we expanded this out into, and that's where that 6 came from. So rather than thinking of it as x squared times x squared times x squared, you do need to get to the point where you just say x squared cubed is just x to the 2 times 3, and that's x to the 6. Because if you have, let's say, x to the 17 raised to the 42 power, you're not going to write out x to the 17 42 times and add all those 17s together. It's faster to just understand that it's x to the 17 times 42. And you're likely not going to encounter weird numbers like that, but that's just an extreme example to say, yeah, you're not going to write something out 42 times. You're not going to have time to write something out 40 times in a test, but even if you were just doing math in a lab somewhere where you have infinite time, not infinite, but you are not going to want to do it that way. The quicker way is just to memorize the times tables, as you did when you were a kid, and then multiply those things out. So the same thing would be here. The inverse of that error is that x squared times x cubed is not going to be x to the 6, because you're not multiplying the 2 times the 3 here, because the base of the exponent, the x, is being multiplied, not being exponentiated. So here, these things just add up. So the easy one here would just be x squared times x3 equals x2 plus 3, and that's going to be x to the 5. And those, I like to say, these are, I don't mean to sound flippant or, oh, you just got to learn this, and if you can't do this, you're not going to be able to do math. These are the fundamental things of algebra that are going to get you quicker. You can always write things out. If you can't do these things fast, you can always write it out. Well, okay, you know, we'll use green for this. I know that x squared is x times x, and that's going to be multiplied by x cubed, which I know is x times x times x, and that will get me to, well, there's 5 x's, so that's x to the 5. If you need to take that time, by all means take that time. Get the answer correct. It's going to behoove you to do it quicker and use the shortcuts like the additions and the multiplications so that you can get through the tests quicker and not run out of time in a situation where you would need it. And then, of course, as you get better and better, it'll just come quicker and quicker. No, we are not using green. Okay, so the third error involving exponents is that 2x to the 3, these are which ones they are. Don't take those big numbers as part of the equation. 2x to the 3 is not equal to 2x quantity cubed. The 2 is just outside. It doesn't. When you see an x3 like that, the cubed is only attached to the x. So the correct answer is just to leave it as 2x cubed. You can think of it, I'm going to put a dashed equal sign, as 2 times x to the 3 if you have to separate the two terms, but you're not going to see it written out that way. So it behooves you to just understand that the 2 is the coefficient of the x cubed term, and it is not cubed itself. If you wanted to, I don't know why you would write it this way, but you could say that that's equal to the cube root of 2 times x, that whole thing cubed. There's no reason to do that. That's just an equivalence that is not needed. But it's there. And then you have, this is a good one. Because this trips many people up too. We always say that when stuff's on the bottom, there's negative exponents, you can bring it to the top using a negative exponent. 1 over x squared minus x cubed is not the same as x to the negative 2 minus x to the negative 3. We can bring things up with an exponent, but the proper way to bring that one upstairs with the negative exponent is that it is equal to x squared minus x3, the whole thing to the negative 1. And that negative 1 does not distribute inside the parentheses to each of the exponents. This is not correct because exponents don't distribute like that. Things that are multiplied do, but exponents don't. Think of it this way, just like we did with FOIL, right? And we'll do red here. X squared plus 1, right? If you take that squared, it's this, or x squared plus 1 times x squared plus 1 is not the same as x squared times x squared plus 1 times 1, right? Those are two different things. You have to do the FOIL method, and you're not going to get the same thing because you have additional terms. Similarly here, this minus 1 does not distribute inside the parentheses. So that is that one. Come on. Going back to black. Okay, so that's that. That's just how it is. And you can write it, you can leave it as that, or you can leave it as that. So now these are errors involving radicals. Now remember, radicals are just negative exponents, so these are probably going to be very similar. The error number 1, so put a little radical there. Number 1. The square root of 5x, or the whatever root, cube, fourth, whatever, is not the same as the 5 times the square root of x. Remember, like we did earlier, and that was my mistake, when we pulled the 3 out, or the 9 out, and I took the square root of it, that's what happens here. The 5, when it pops out, now, this is correct, the square root of 5x is equal to the square root of 5 times the square root of x, but it is not equal to 5 times the square root of x. You can simplify things this way, where, say, 16x square rooted is going to be equal to 4 times the square root of x, because I took the 16 out. The intermediate step here would be, this is the same as the square root of 16 times the square root of x, and that's what led me to that one. That is correct, but the 16 does not just come out of the radical by itself. That's the error there. Okay, the second error is the square root of, there's a good one, x squared plus a squared is not equal to x plus a. And I would add, okay, what happens here is that people assume that the square root would apply to these things and distribute. Just like we said earlier, the exponents don't distribute. So if you thought of this as x squared plus a squared to the 1/2, we said that would not distribute, and that's correct. So that's not how it works. I would also add that this is not equal to the square root of x plus the square root of a. That's not how it works. When you have summed terms under a radical, they must stay by themselves. Now, an easy way to prove this to yourself is, let's say I have the square root of 1 plus 1, right? That's going to come out to be the square root, in the wrong way, right? We're going to put in not equal here, right? Square root of 1 plus the square root of 1, and that's going to be 1 plus 1, and that's going to be 2. Well, the square root of 2 is not equal to 2. So we know that's incorrect. The other one that would be the one here is going to be that the square root of 1 plus 1 is equal to the square root of, or the way they do it is just 1 squared plus 1 squared is going to be equal to this, 1 plus 1, and that's also going to be here, the square root of 2 equals 2. That's just because we're using ones, but it's easy to see that those are not equal. So be careful of that mistake. What would be the correct answer here? You just leave it as this first one. Go back, blue. There's no simplification. That is in its simplified form. Don't worry about that. They have another one here for number 3, where the square root of minus x plus a, and what they've tried to do is factor the negative sign outside the radical, and they did it correctly. They distributed it right. You have x, positive x minus a. Well, that doesn't work, because although you can distribute a negative sign into a parenthetical equation, right? That doesn't work as soon as the parenthetical equation has an exponent. That should ring alarm bells, because you can't do that. A negative sign put into a squared equation, for example, would require that you could square to something negative, right? And it doesn't work that way. So just don't mess with negatives and stuff in the parenthetical equations. Actually might work for that one, but I just don't want to mess with it. You can't factor it out of a squared equation for this reason. If I say, let's just look at an example. This is going to kill us long before we get to the final example. But let's look at this. So I have square root of, let's use 4 and negative 4, and we'll say minus 2, for example. And I say, okay, well that's going to be the same as negative 1, right? I factor out a negative sign, which is the same thing as multiplying by negative 1, times 4 plus 2. And I can put that in the square root. Now, I say these two things are equal, minus 1 times the square root of 4 plus 2. That is all correct, except that what the heck is the square root of negative 1? That doesn't make any sense. And so right there, you wouldn't be able to factor it out of the radical, because the square root of negative 1 doesn't make any sense. Then, once I factor it out, that would mean something would have to square root to something negative, and that it just doesn't work. So that's why this is incorrect. And you would just leave it as this. Now, you would say, well, why do we have negative x in there in the first place then if we can't have negative square roots? That the square root of negative 1 is impossible. It's an imaginary number that you'll come to find out later. But the reason that negative x can be in there is, let's say x is 12 and a is 35, right? Well, a negative 12 plus a positive 35 still ends up being a positive number, and you don't have to worry about the square root of negative 1 at that point. So there are domains for which this equation is valid. It's not the presence of the negative sign on any term that invalidates any of these specific things. Okay, so now we're going to move on to the next one, which is errors involving canceling things. Okay, so good one. So here we go. We have a, well, let's see. We're going to write a squiggle plus another squiggle over a squiggle, and we're going to say canceling. That's going to be our errors on canceling things. The first one would be a plus bx over a, and that is not equal to 1 plus bx. What you've done here, got the 1, is either you canceled the a and you just thought you could get rid of the denominator completely, and you know that this has an end up 1, or you canceled the a and okay, there's two forms. Either this person, this theoretical person that got it wrong, canceled this a out to a 1, or they canceled it and just got rid of it. I'm going to do a little dunk, like it disappeared. And both of those are wrong, because you could say that this is equal to 1 over bx plus 1, or over 1, sorry, 1 plus bx over 1, or it's just equal to 1 plus bx. Either way, you end up with the same thing specifically for this question. The way you would know is like if you had 2a on the bottom, and you'd know if they left the 2 there, then what they were thinking was that they could cancel the a out, and the denominator would remain as a 2, or they just got rid of the 2a entirely. So if we rewrite this I know I'm explaining this a little weird, but let's say it's 2a plus bx over 2a, right? The first person in our theoretical example thought that the 2a cancels the 2a completely, so it just disappears. This is going to be the disappear route, just pops out of existence, and you have 1 plus bx. That's how they write it. The other person, I'm sorry, this is actually a. Sorry, I'm having trouble with my mouse here. Okay, this is a plus bx over 2a. And what this person in the disappearing thing has done is they think that the a... No, I had it right. The 2a actually disappeared, right? And so it just blinked out of existence. The other person thinks that the 2a truly canceled, but it canceled out to a 1. I guess it ends up being the same thing. It ends up being a 1, I'm sorry. A 1. And so, like, you have a 1 here and a 1 here because they cancel out. Yeah, I guess there's no other way it would cancel out. Okay, I'm going to erase all that. Ignore all of that because it ends up being the same. But those are the two lines of thinking. That it disappears or it cancels to 1. Both of those are incorrect. All of that is to say that both of those are incorrect. The thing is that to cancel, the a would have to be present in every term on the top, because what you want, so I'm going to write in red here because this is not what we're talking about. We want a, plus b x a plus ac or something over a. Well, what you would think of is that in the first case I can factor an a out of everything because I took this a out, I took this a out, and I took this a out, and I factored it into this single a, and now these a's can cancel out to a 1 down here. But if that a doesn't exist in that term, then it can't cancel out. And that's what this person has done here. So the correct answer is that you just leave it as it is because you cannot cancel everything. So what you could do, if you really wanted to do it this way, is you have a over a plus bx over a, and then you could get to 1 plus bx over a and still do some canceling, but that's not necessary. I would just leave it like this. That's an okay fraction. A little bit long-winded, but I'm trying to think of why you would make that mistake. There you go. So a plus ax over a, that's another good one. I guess it's a similar one. I don't know why anyone would make this one either. I guess that's what's my problem is I can't grasp why people would make these mistakes. This is not equal to a plus x. What this person did here is they canceled those two a's and left this one. Exact same thing as the first one, so I'm not going to go through any extra explanation. Remember here, like we said before, there's an a in every term, so those three a's would cancel out, and the correct cancellation would look like this. You'd have a plus ax over a. You would factor that a out of here, and then you would cancel, and you'd be left with 1 plus x. And the last one involves cancellation would be that 1 plus x over 2x is not equal to, this is weird, 1 plus 1 over x. I have no idea why anyone would make that mistake. That is weird. You're canceling the x with a 2, and that makes no sense. Okay, whatever. The correct way is, of course, 1 plus x over 2x. The x's cancel out. You get 1 plus 1 over 2, which just ends up being 3/2, or 1 and 1/2. Weird. Okay. But I guess that's an error people make. The way he puts it in here, after all of those errors, is for many people a good way to avoid errors is to work slowly, write neatly, and talk to yourself. Each time you write a step, ask yourself why the step is algebraically legitimate. For instance, when you write 2x over 6 equals 2 times x over 2 times 3, and you cancel out the 2's, equals x over 3, you can justify your work because dividing the numerator and denominator by the same non-zero number produces an equivalent fraction. It's a long way to say that, yeah, you can cancel those 2's out. But he is correct. If you just write those things out and go slowly and walk yourself through the problem, is what he means by talk to yourself, you should be able to spot errors. A lot of times, especially during tests, you're going to have the urge, you're going to be tempted to go quick because time is a factor. If you find yourself making a lot of those mistakes, take your time. It's better to finish 90% of the test and get it all right than finish 100% of the test and get it half wrong. So just be slow, be methodical, be deliberate. Okay, so now we're going to go into, he calls it the algebra of calculus. And the reason he calls that is because in calculus it is often necessary to take a simplified algebraic expression and unsimplify it. So we're going to look at these things. So the first one, he calls it unusual factoring. So instead of, and a lot of these are things we've already talked about. So instead of 5x to the 4th over 8, you would write it as 5 over 8 times x to the 4. And like we said in the last chapter, that's because you're going to want to use the 5 over 8 as a coefficient, and you're not concerned with how it looks with the single term on the top and then the 8 in the denominator. That's just the coefficient is more important in that case. So you'll see it written both ways. It's just up to you to know that both of those things mean the same thing, and that's why he's giving this part here. You have x squared plus 3x over negative 6. And here he's written it as 1 over 6 negative x squared plus 3x. Again, we want the 1 over 6 to be the coefficient of that term because we intend to cancel it out later, the term, or we intend to use the 1/6, something. So you'll see it written that way. One thing that you will see a lot, especially as you get into geometry and algebraic geometry, is something like this. So you've come up with an answer that says 2x squared minus x minus 3. Algebraic geometry, i.e. like the general form of a sphere or some crap like that, or calculus, doesn't usually like the first term to have any coefficients. So sometimes you'll see like an a being the generic term for the first term of the first coefficient of the highest term, and other times you won't see a coefficient on the highest term. They expect you to divide that out through everything. So, for example, here, you would factor out the 2. Now you're going to say, wait a minute, there's no 2 in that second term. How are you factoring out a 2? Well, there is a hidden 2 there. So here, 2 comes easily out of that term, but we have to make this one into a half term. And then here, we also have to make that in a half term. And I've skipped a step there for the beginners, but what you would be thinking is that 2x squared has a 2 in it. X doesn't have a 2 in it, so we have to give it a 2. Well, x times 2 divided by 2 is still x. So you could say that this is 2x squared minus 2x over 2 minus 3 times 2 over 2. So we have 3 times 2 over 2. And so now I can take a 2 out of each of these things, factor it out, and I'm left with x squared minus x over 2 minus 3 halves, and which is what we got here. Again, you'll see this because in calculus you may want to deal with a coefficient at the head of everything, or like say in algebraic geometry, you will not want to see a coefficient on the first. That's not a 0. You won't want to see a coefficient on the highest order term, so they will just take it out and do stuff with it. Okay, so that's that one. You have what did he do here? I don't even know what this one is, but we'll go through it. X over 2 times x plus 1 to the negative 1/2 plus x plus 1 to the positive 1/2. And you will see that written in his thing as x plus 1 to the negative 1/2 over 2 times x plus 2 times x plus 1. There's no way to write it like this, because here you would just distribute this 2 and you'd have x plus 2x, which is 3x plus 2, because the 2 distributes there and then the 2 distributes there. There is no reason to write it like he did that I can think of, but he has a reason. He says factor out, factor with least power. Okay, whatever. I'm going to leave that one as an exercise to the reader because I have zero idea what he's trying to do there. Okay, so inserting factors and terms. Sometimes you'll see that. So 2x minus 1 to the third power is going to be the same as 1 over 2 times 2x minus 1 to the third power times 2. It just says multiply and divide by 2. It's a useful calculus form. I don't know, maybe we'll see that in calculus. I doubt it. We have 7x squared times 4x cubed minus 5 to the 1/2. And then it's even weirder. He's got 7 over 12 times 4x cubed minus 5 to the 1/2, and then times 12x squared. And it just says multiply and divide by 12. I have no idea why you'd want to do that, but okay, that's one way to do it. He has some examples, maybe we'll see it there. Okay, 4x squared over 9 minus 4y squared equals 1. Okay, so this one is a special example. You don't know why yet, but this one should be written exactly like we talked about earlier. X squared over 9/4, and notice how he took the 4. The top of the top becomes the bottom of the bottom, and he took it down to the bottom. Oh my goodness. And that's minus y squared over 1/4, and that's equal to 1. The reason you would write it this way has to do with the equation of a circle, but again, you'll notice that there are no coefficients on the highest order terms of each of the variables. So that's one of the ones that you will see later on. I know that for a fact. So here you have x over x plus 1. Then you have you're gonna take a 1 and you're gonna add and subtract on the top a 1. So you have x plus 1 minus 1 over x plus 1. And what this is going to come out to be is, like we did before, these two terms will cancel out on their own, but you'll still have this term to deal with. So what we'll end up with is 1 plus, or minus rather, 1 over x plus 1, which is a weird way of writing it, but in some instances it might be useful. Similar to the one we had above. We have 9 over 5x cubed. You may want to write that as 9 over 5 x to the negative 3. Polynomials can be mostly of positive exponents, but sometimes you'll have a negative exponent in your polynomial, and it will be beneficial to write it as its own negative exponent with the coefficient 9/5 as its own coefficient, not an integer, but a real coefficient that has non-variable, I guess a constant coefficient is what I'm trying to say. Similar here, we would do 7 over the square root of 2x minus 3, and you're going to write that as 7 times 2x minus 3 to the 1/2 negative, because you'd want that as its own thing. And then this one I do all the time because for me it's simpler terms. For a lot of people it's not, but it helps me to think. And so as I'm solving problems, you may see me write this way. Again, this is useful for calculus. I did this, I don't want to say, oh, I did this before I got into calculus. It made more sense to me. You need to write, remember, math will always work out to the right answer if you're doing it right. I'm not saying that anything you do will work out, but if you apply the rules correctly, you're still going to get the same answer whether you take path A, B, or X, right? So here he has, this is writing fractions as sums. And the first one he has is x plus 2x squared plus 1 divided by the square root of x. Now that you can leave as is. How would you, a lot of people will multiply a square root of x at the top of the bottom and then you still have x on the bottom. Okay, so let's write that way. This is the red way because this is the way that most people will do it to get rid of that radical in the bottom, because people don't like to see radicals in their fractions, especially in the denominator. So then you'd multiply the top and the bottom by the square root of x. So the bottom is just going to become x, because the square root of x times the square root of x is going to be that thing squared, which is just x. So we're going to say times that, and then we're going to say equals. So you'd have x square root of x plus 2x squared square root of x plus square root of x, because x times 1. That's fine and dandy. It gets rid of the radical in the denominator, but there's a simpler way to write that may be useful in calculus. We're not going to multiply anything. We're just going to divide. Remember that because we have a sum on the top, we can split the fraction into a sum like this, plus 2x squared over square root of x plus 1 over the square root of x. But we would not stop there, and this is why I say this. I would do this because it would make more sense to me and be more concise with what I'm looking for. X divided by the square root of x is the square root of x, which we're going to write as x to the 1/2. 2x squared divided by the square root of x is going to be 2, because the coefficient doesn't change, times x squared times x to the negative 1/2. Remember that because we have two things being multiplied together that are exponentiated, we can add them together, and this would actually work out to be x to the 3/2, because it's just going to be 2 minus the 1/2. And then at the end you'll have plus 1 over the square root of x, which is just going to be x to the negative 1/2. and that will be useful because you're going to be using the x and their exponents as polynomial factors, and so you'll want the x's to be in their lowest form and not have to deal with that x in the bottom, and this is the way you would do it. And that's why to me it always made sense, because x divided by the square root of x is just going to be the square root of x, so why wouldn't I write it that way? So you can simplify things that way. Again, I hesitate to give you that advice because, again, these stickler algebra teachers might count off for writing it in that form, even though it's completely correct. And you just have to argue with them that, hey, this is correct. They're looking for it in maybe that upper form or something weirder. But math works. If I were a video editor and this weren't live, I would throw Mr. Incredible saying math is math up here. But yeah, arguing with teachers is a favorite pastime of mine. Okay, so you have 1 plus x over x squared plus 1. You're going to write that as a sum, and you're going to take it to, you're just going to factor it out like we did that one. So you have 1 over the square, x squared plus 1 plus x over x squared plus 1. And why would you do that? Sometimes you're going to see these terms and you're going to need to cancel it or something like that. It's just expanding it out to its own type of fractions. Or you may treat x squared plus 1 as its own term, call it y or w or something, and you may want to write it that way for some reason. This one, he does this for some reason, 2x, similar like he did in the last one, not the last specific one, but the last section of stuff. He has 2x over x squared plus 2x plus 1, and he has rewritten that as 2x plus 2 minus 2 over x squared plus 2x plus 1, and I think he's getting ready to cancel something here or do something with it. So here he has, yeah, he's done it this way. He rewrites this as, why would you do it that way? Okay, 2x plus 2 over x squared plus 2x plus 1. X squared plus 2x plus 1 is the same as x plus 1 squared, but he writes it this way. We'll see why he wrote it that way. Probably going to show up in one of the examples, but I don't know why you would simplify this one and not this one, but we'll see. And then he has x squared minus 2 over x plus 1, and he's written this as x minus 1 minus 1 over x plus 1. What he's done there is that he has factored out that equation. That's not how it works, though. Oh, he split the, that's what he did. What? Okay, he just divided it. What he's saying here is actually the result of long division. And I don't know that I went over that, but maybe I did. You have, yeah, he doesn't go over that until section 3.3, for real? Yeah, you won't see that until chapter 3, section 3, but he's actually used long division. That's why I don't remember going over it, where you have x plus 1 on the outside, and you do long division of x squared minus 2. I don't know that I want to go through that now, but you would do that. So you would do, 1, and then you'll get x plus 1, and then you divide this out, and you get remainders and blah, blah, and you have to work it out till you get to a specific thing. We'll refer to that in section 3.3. So don't worry about how we got there, but that's how he wrote it out. And then he did another one, partial fractions, to get this one. And we'll see that one later as well, x squared minus x minus 6. Partial fractions becomes very important in calculus, so you will need this later. 1 over x plus 2. And I will link to either this part of this video or where you see this in the final presentation video when we get to partial fractions in calculus. So we can go over it again. He's going to go over this method in section 4.3. So I'll link to both of those places. So okay. So those are all the errors and algebras of calculus that he uses. And then he does the examples, so let's go through some of these examples. Let's see. So factors involving negative exponents. So he says, okay, so that's not right. That is also red. Okay, so example 1. Factor x times x plus 1 to the negative 1/2 plus x plus 1 to the 1/2. Okay, remember that you add exponents. When you are factoring, it says when multiplying factors with like bases, you add exponents. When factoring, you are undoing multiplication, so you would subtract exponents. And so here, he has some long drawn-out thing here. Yeah, I guess you could do that. Okay, so this is one way to do it. Remember above we said that x divided by the square root of x is just going to be x to the 1/2, because this is the same as x to the 1 over x to the 1/2. So when you divide, remember you subtract. This is the same thing as x to the 1 times x to the 1/2 negative, and so you would add those things together and you'd end up with a positive 1/2. We're going to do something similar here. So we have this whole big thing, x plus 1. Give me the eraser. And I'm going to call this guy y for now. So we have x times y to the negative 1/2. And we have y to the 1/2. So what I'm going to say is that I can take out a y to the negative 1/2 from this thing. And from here, it just becomes a 1. So you have x, right? And then from here, if I take out a negative 1/2, recall this guy yet again, I'm going to say that this guy turns into itself. So we have x plus y, because we factored out a negative 1/2. The way to think about it, if you want to like put a thought bubble here, is that for the second term, we have y to the 1/2, and we're going to multiply it by y to the negative 1/2 over y to the negative 1/2. This guy is going to come to the top, because a negative exponent in the denominator is going to move to as a positive exponent in the numerator. So you have y to the 1/2 times y to the negative 1/2 times y to the 1/2 again, because this guy migrated up here. Y to the 1/2 times y to the 1/2 is going to be y, because it's the same thing as saying the square root of y, not x, times the square root of y. That squared is just going to be y. So you end up with a y to the 1, if you want to think of it that way, and you still have this y to the negative 1/2, which allows us to factor that, still have y to the negative 1/2 out, like we did, I'm sorry, not there, but here. And we're stuck with these two guys, which ends up being y. So you end up with x to the y. We'll leave that there. If we factor back in what y really means, that's x plus 1 to the negative 1/2 times x, well, that's the ugliest x, plus x plus 1, right? And then we get 2x plus 1. So we get x plus 1 to the negative 1/2 times 2x plus 1. And that's how you would factor them. Yeah, I guess. That's what he gets. But yeah, that's how you would look at it. So that's one way to do it. Okay, so example 2. Let's make one more column here. Example 2. Rewriting the fractions. He doesn't tell you why he does this, but yeah, looking at the one that we have 4x squared over 9 minus 4y squared, and that's going to equal 1, but we want to rewrite it. We want to rewrite this, and how he's going to do it is, first of all, we recognize that just like we can take things from the bottom and move them to the top if they are denominators, we can take things from the top and move them to the bottom in a similar way. So here, and okay, again, and we will talk about this as we go through algebra and stuff like that in the subsequent chapters. I talk about moving things. So here, I think in my brain, this is how it works. X squared times 4 over 9 becomes, this is my symbol for moving things, x squared over 9 divided by 4. The 4 has moved to the bottom. If you wanted to accomplish this in an algebraic way and not think of moving things, that's just how I think of it, and it makes things work for me. It may not work for you. You might think of it this way, and this will work for you. Either way, again, the math works out. Where's Mr. Incredible? Math is math. The other way to do this would be to think of, that's one way, this is the other way, x squared times 4 over 9. You would say, I'm going to multiply the top by 1 over 4 times 4x squared. Whatever I do to the top, I have to do to the bottom. So I have 1 over 4 times 9. Well, these 4's cancel out, and I'm just left with x squared in the top. And now I have on the bottom 9 divided by 4. That's the proper way to think of how that's happening. The movement type stuff is just a shorthand for what happened right there. So whatever way works for you, you get to be comfortable with that. Okay, so those are the two ways you would do it. So he had that, and so that's how you get that one. So you have, he wanted to write x squared over 9/4 there, right? And here we do a similar thing, minus y squared, and you have the 4 moving to the bottom, but when it does, it becomes the denominator of the bottom over 1/4 down there. And again, the reason you would want to do this, you'll see later, is the equation of a circle. The rest of it is just stuff, and he doesn't explain that weird one that we saw earlier, so I'm not going to explain it either. And then he goes into the problems, and then we're now on the final chapter of this section, the graphical representation of data. And I apologize much in advance because most of what I do is graphical representation of data, and I have nothing prepared to show you beautiful things here, so I'm going to draw stuff. But when we get to the presentation or the video that covers these chapters, it will be a lot nicer, and you will see actual charts done by software rather than hand-drawn crap from me. Okay, so the first thing he introduces here is the Cartesian plane. And the Cartesian plane is named after René Descartes. And I'm going to bring something up a little quickly to talk about René Descartes. So René Descartes was a French philosopher and a scientist. We're going to tear this window off. And I hope I don't hit any copyright crap. This is for education, as a defense for fair use. René Descartes is the guy that came up with the Cartesian plane. So we're going to pop into Wikipedia here, not for him, but going from him, we're going to say Cartesian. And we want the Cartesian. I guess we don't have a Cartesian plane, but we do have the Cartesian coordinate system. And this is what he's talking about. Just as you can represent real numbers by points on a real number line, you can represent ordered pairs of real numbers by points on a plane called the rectangular coordinate system, or the Cartesian plane, after French mathematician René Descartes. And he lived in the early 1600s, so this stuff is super old. So I just wanted to show where that came from. So the Cartesian plane is formed by using two real lines at right angles to each other, as shown in a figure that you can't see, but I'm drawing. So here you go. This is what we call the x-axis, and this is what we call the y-axis. X and y just being two randomly chosen things that we normally use as variables in algebra. And when they say ordered pair, the order of the pair is x and then y. So you have an x and a y, and they usually write them in parentheses like that. And so when you see parentheses x comma y, that's referring to a point on the plane. So for example, if I look at my old number line, I had little hashes that told me where the numbers were. Similarly, I have here. And it is convention that the y-axis intersects the x-axis where they both are 0. So that point is 0, 0. And if I wrote something like 3, 4, then I would say, well, the x is 3, so I move out to 3. Here's 3. And then I move up to 4. 1, 2, 3, 4. But I do that over here where the 3 was, because I move from 3 up to 4. And this is the point 3, 4. The Cartesian plane is formed by using two real lines intersecting at right angles, as shown, blah, 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 the point of intersection. This 0, 0 is referred to as the origin, because that's where everything starts from. That's where you count the 3 and the 4 from. That's where they originate. But again, it is conventionally that they intersect at 0, 0. And that the two axes divide the plane into 4 quadrants. You have quadrant 1, and then going this way, we say this is quadrant 2, and then this is quadrant 3, and this is quadrant 4. You'll see that in quadrant 1, you'll have positive, positive. In quadrant 2, you'll have negative x but positive y. In quadrant 3, you'll have negative, negative. And in quadrant 4, you'll have positive x but negative y. Each point in the plane corresponds to an ordered pair. I've been doing integer points 3, 4, because that's what's very simple. But there's no reason you couldn't have pi, comma, 6/4 or something like that. Every point on the plane is represented by two real numbers in the real world. The x-coordinate represents the directed distance from the y-axis to the point, and the y-coordinate represents the directed distance from the x-axis to the point. This is a fancy way of saying that if you look at the first number, like we did here when I said it was 3, you would count 3 units from the y-axis to the point, wherever it is. So every point along this line that I'm drawing here is 3 units from the y-axis. So they're all going to have the first coordinate be 3. When you say that the second coordinate is 4, you would count 4 units from the x-axis, and that's where you're going to end up. But this will trip people up because the 3 is how many points, how many hashes along the x-axis is, so it's the distance from the y-axis. And so this being the x-coordinate, but the distance is from the y-axis, sometimes throws people off because you're involving the 2 different axes. That's why I like to think of it as along the x-axis, not from the y-axis, but it'll give you that distance. So, for example, he says plot the points. Example 1 is plot the points -1, 2, 3, 4, which we've done, 0, 0, 3, 0, and -2, -3 on the Cartesian plane. Okay, so I'm going to draw my little plane here in black. Draw hash marks 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And I'm going to start plotting the points. Okay, so we're going to plot the points in red. So point -1, 2 means that we're going to go -1 along the x-axis and 2 positive along the y-axis. So there's one there, and there's 1 there. So here's what we're going to say that's 1, that's 2. So that point corresponds to this point right there. That is -1, 2. 3, 4 we've already done. We jumped 3 along the x, and then we do 1, 2, 3, 4 up. This is 3, 4. 0, 0 is the origin, so we know where that one is. 3, 0 is 1, 2, 3 along the x-axis, and then 0 along the y-axis, so nothing up or down, so this is 3, 0. And then -2, -3 is we go -2 in the x direction and -3 in the y direction. So this point would be -2, 3. And if we just looked at those without all their connecting arrows and little squiggles to show the distance we moved, this is what it would look like. And I'm going to do a different color for each one of them. So blue is going to correspond to this one. We have -1, +2. Green is 3, 4, which we've done many times. Yeah, that's green. Red is going to be 0, 0, which we said was the origin. I'm going to say orange is going to be 3, 0. And I'm going to say yellow is going to be 2, 3. Well, yellow is not visible. I'm going to say purple is going to be 2, 3. Or -2, -3, right? -2, -3. So that's where all those points would lie. He talks about sketching a scatter plot. That's an easy one. What a scatter plot is, I'm not going to go through the example, but you'll have a table of data where you say like, okay, here is make a new graph. So this is example 2. We're not going to go through the example, but I will in the presentation. I have some table that says at this time from the start of a race, the distance that a car traveled in the race is this. So you have 1, 2, 3, and then the distance is 6, 12, or 21, or whatever. And you would just use these coordinates as ordered pairs: 1, 6, 2, 12, 3, 21, and then you would sketch a line through those points to show the line is not really part of the scatter plot. You would just see the dots, and so you'll see something like, instead of distance, let's use speed, velocity, right? So normally the car starts out slow, it starts speeding up, and then it tapers off, and they're going pretty fast, but they stay at the same speed for a while. So you'll see just points along this curve showing you how fast the cars are going. That's a scatter plot. Again, we'll look at those more in depth as we get to the presentation, and definitely in some of the later classes like stats and some of the data visualization type stuff, which I will likely dip into that too, because that's what I do now. Okay, so one of the most important things that will come out of this is the next two sections, which will finish the chapter, thank the Lord here, and but we're going to look at both the distance formula and the midpoint theorem, the midpoint formula. Okay, so if you remember, I don't know when you were taught this, but you call your early education, and you remember your Pythagorean theorem. You know that a squared plus b squared equals c squared. There's plenty of proofs. I'm not going to go through a proof. We're just going to say that this is an axiom that we hold as true. If I look at some point on the plane, for example, our favorite 3, 4, right? So I have 3 units down here and 4 units up here. What is the distance that that point is from the origin? The generalized form of this is, what if I just want the distance between any 2 points in the plane? So we're going to look at both of those. And in fact, we'll do his version, which he has it this way. And the reason is this. He wants to show this as a right triangle. Okay, so let's look at the distance between this guy, and then we'll do his example 3. And I want to put example 4 in the presentation, but it's not necessary here because it's just additional stuff of the same thing. But it would be, how do you verify that something is a right triangle? So that will be in the presentation if you're interested in it, but there's no reason to go through here. It's just an application of the distance formula. Okay, so if we just be naive, and so this, I'm going to circle X in because I want to put it in the presentation. But right now, this is example me, so I'm going to put example M for me because this is not in here. But I want to look at this distance here, and we're going to do it naive, meaning we're not going to use the distance formula yet. But if I remember my Pythagorean theorem, and I take, as he said, that these are the directed distances from the x-axis, meaning these are the shortest distances from the x-axis or y-axis, meaning that if you drew a line from that point to that axis, that would be a perpendicular line. That's why they use that terminology. This line would be perpendicular, and then this line would also be perpendicular, right? Then I know that this is 3 and this is 4 units, and I can draw that triangle. And if we recall our Pythagorean theorem, that the distance is a 5. That's what a classic 3, 4, 5 triangle. So I know that this point 3, 4 is 5 units from the origin, simply because I've applied the Pythagorean theorem. So how could I apply that Pythagorean theorem for 2 arbitrary points? Well, the way they do that is they introduce the distance formula, which is d, distance, equals the square root of x squared, or I'm sorry, x2 minus x1 squared plus y2 minus y1 squared. And why does this work? Remember that these are the directed distances from these axes. So, for example, in this equation, we know that this point, we're going to call this x1, y1. And we're going to call this x2, y2. Just two random arbitrary points in the plane. However, I know that x2, y2 is x2 units from the y-axis. And I know that x1 is x1 units from the y-axis. So this line segment here is x2 minus x1 units from, that's the line segment length. Not from anywhere, that's just the line segment length. And similarly, this is y2 minus y1, that line segment. So I know that the base is this length, and the height is this length. I can say I know this is a right angle triangle because it is by definition that the x-axis and the y-axis are at right angles. So now I can apply Pythagorean's theorem and say that b squared, base squared, plus height squared, that's an h, that's an ugly h, square root is the answer to what the length of this line is. So the distance formula comes directly from Pythagorean's theorem. And so we write it like this. X squared minus x2 minus x1 squared plus y2 minus y1 squared, and then that's going to be this way. So let's look at 2 points. He has here, for example, 3. We're looking for minus 2, 1, and 3, 4. Our favorite 3, 4. Okay, but 3, 4 is 5 units away from the origin. That doesn't mean it's 5 units away from everything, so these are 2 completely unrelated points. But we want the distance between those 2. Well, right here, it's very simple. We have a formula that needs to be memorized, and then you just plug and chug. So we have x2 is 3. And this is x2, y2. This is x1, y1. So we go x2 minus x1 squared, and I know I have 2 minuses there. I'm gonna cancel it out later. Plus y2. I'm gonna write a y. y2 is 4 minus y1 squared, and this whole thing square rooted. So here we have 3 minus a minus 2, which is the same as 3 plus 2, which is the same as 5. Here we have 4 minus 1, which is the same as 3. So we're going to say that this is the square root of 5 squared plus 3 squared. That's going to be 25, square root of 25 plus 9, which is going to be 34. And the distance is going to be the square root of 34. And that turns out to be somewhere around 5.83 and blah, blah. So let's pop out this midpoint theorem and be done. So the midpoint formula, it's very simple. You just divide the distance by 2, thankfully. And so d divided by 2 is going to give you the midpoint, the distance of the midpoint. Actually, it has nothing to do with d, but you'll see something similar. The midpoint is going to be given as the average values of each of those. So you have x1 plus x2 over 2, and y1 plus y2 over 2. So for some random segment, And this is going to be very helpful in interpolation. So this is another formula that you'll likely need to memorize. If we want to look at I'm going to do example 6 in the presentation, but we're going to do example 7 here. Example 7 is estimating annual sales. So if I know that on a graph for the year 1992, yeah, this book's kind of old, I know that we sold 132 ice cream cones. That's what he has in here. Of course, he's talking about million. He's talking about Ben & Jerry's annual sales, so I'm going to say 132 ice cream cones, even though it's million. I know that's there, and I have, in 1994, we have 148.8 cones. Somebody got a 20% discount on a cone there. Those are 2 points on a graph, a scatter plot. Well, what would be the sales for 1993, assuming that it grew linear like that? So that would just be the midpoint of those 2 things, and you'd have 1994 plus 92 divided by 2, which the average, of course, is going to be 1993, which is what we wanted. But then for the y, we have 148.8 plus 132 divided by 2. 148 plus 132 is 180.8. Divided by 2 is going to be, 280.8. 140.4. And that's going to be your midpoint, 140.4. So we can estimate that the sales are 140.4. Now, if we want to do example 6, very simple. It's going to say, what's the midpoint of the line joining minus 3, and 9, 3? Weird. What's the midpoint of that line segment? Very simple. 9 minus a minus 5 divided by 2, comma 3 minus a minus 3 divided by 2. Well, 3 minus a minus 3 divided by 2 is going to be 3, right? I'm sorry. These are plus. I keep thinking of the distance formula. Sorry about that. Okay, so we got 9 plus a negative 5 over 2. And then we have 3 plus a negative 3 over 2. 3 plus a negative 3 is just going to be 0, so that's going to be 0. And then 9 minus 5, or 9 plus a negative 5, is going to be 4 divided by 2 is going to be 2. And the midpoint of that is just 2, 0. If we draw a graph, just to make it visible, we have 9, 3 way over here. We have 5, negative 3, negative 5, negative 3 over here. And zoop, we go here. Oh, that's very poor. Okay, you know what? I'm going to make that much better. Here's that. 1, 2, 3. 1, 2, 3. Let's say that's 5, and that's 10, and that's 5. So we have 5, negative 3. Negative 5, negative 3 here, and 9, positive 3 there. We draw a line, and zoop, oh, look at that. It hits the axis right near the middle, actually exactly in the middle, and it's 2, 0 there. So it looks correct because it is correct. And that's the midpoint there. So that is everything you need to know to start algebra. And so we will start algebra very soon. I'm probably going to have another live stream of me fumbling around with Manim and other animation type stuff, or PowerPoint, to see if I can get these presentations to look good. But I probably will have more live streams of this stuff so that I can get the presentation, like, topics correct. But thanks for joining me, and we will see you next time.